Hello, my name is Elena Dubrova. I will be presenting the first part of the talk, How Deep Learning Helps Compromising USIM. The second part will be presented by Martin Brisfors. I will start with a motivation and a background on protocols and algorithms related to USIM cards, Authentication and Key Agreement, MILENAGE, and Advanced Encryption Standard. I will then present our equipment and describe how we captured power traces and located the point of interest. Then Martin will describe the training process and how the USIM key is extracted using the resulting CNN model. Then we will show a video of a USIM attack and conclude the talk. A USIM is a type of smart card. It contains all necessary information about the subscription at the home network, including a long-term secret key K, which is pre-shared with the home subscriber server, an international mobile subscriber identity, EMC, and a number of other parameters defined by the operator, including an operator variant algorithm configuration field, OP, which is used for all subscribers. All cryptographic operations which involve the secret key are carried out within the USIM. 3G, 4G, and 5G security relies on the USIM key. If this key is stolen, the attacker can clone the card and receive subscriber text and calls, or impersonate the subscriber. Alternatively, the attacker can impersonate the network and potentially extract important information from the subscriber. It is known that the secret key can be extracted from some USIM cards using correlation power analysis. In this talk, we will present you a more advanced approach based on deep learning. As in previous work, the target is the Authentication and Key Agreement protocol, which we review next. Authentication and Key Agreement is a challenge response multi-party protocol based on symmetric key cryptography. The involved parties are a database in the home network storing the subscriber credentials called the Home Subscriber Server, HSS, an authenticator in the serving network called the Mobility Management Entity, MME, and a mobile entity equipped with a USIM card. ACA is initiated by the MME, which sends to the HSS a request for an authentication vector, AV, associated with the subscriber of mobile entity. The HSS responds with an AV consisting of the following four parameters: a random value rand, a network authentication token AUF, the expected response from MEXRES, and the session key KASME, which is established in the mobile entity and MME when the ACA run is completed. When the MME gets an authentication vector, it initiates the authentication procedure with the mobile entity by forwarding the rand and AUF to the mobile entity. It in turn sends them to the USIM, which verifies the authenticity and freshness of the AUF and derives the response parameter res, the cipher key CK, and the integrity key IK from the master key K, rand, and AUF. They are computing using MILENAGE algorithm, which we review next. MILENAGE computes these 7 functions shown below related to the Authentication and Key Agreement. Our point of interest is the block denoted by EK. Note that MILENAGE contains 6 such blocks. EK represents a 128-bit block cipher. We will attack the first one, this one. Its input is a random challenge rand XORed with a parameter called OPC. OPC is computed as shown in this box from the key K and the OP parameter defined by an operator. FreeGPP recommends advanced encryption standard for implementing the block cipher in MILENAGE. Here is a block diagram of advanced encryption standard keyed with a 128-bit key. It consists of 10 rounds. All rounds except the last one repeat the following 4 steps: subbytes, shift row, mixed column, and add round key. The key K is XORed with a plain text before the first round. The 10 round keys are derived from K using the key expansion algorithm. Our measurement setup is shown on this slide. This board is a chip whisperer which is used to measure power consumption. The red board is a generic platform which can be used with multiple targets plugged into this U-shaped connector. The plugged green board is a custom smart card reader called Layla. Susmocom USIM cards are used as an attack target in this attack. These cards are compliant with 3G and 4G standards and can be used with any core network. They are shipped with a factory default car-individual random key K and OPC. However, they are fully reprogrammable and the user can reprogram key and OPC. In our setting, a PC plays the role of MME. To initiate the authentication, the PC communicates with the USIM and calls MILENAGE with a random challenge run as a seed. At the same time, the PC sends to the chip whisperer a trigger signal to start capturing the power trace of the USIM. This slide shows a full USIM power trace for one MILENAGE call. We will further zoom this area shown in black square, which represents EES encryptions. Now you can clearly distinguish 7 repeating blocks. Note that MILENAGE contains only 6 encryptions. However, the encryption is also used to compute OPC. Since it wasn't clear which of the encryption blocks corresponds to the start of MILENAGE algorithm, we carried out correlation power analysis for the first and second blocks in the trace to figure it out. Next, I will show you how correlation power analysis is done for the MILENAGE algorithm. In MILENAGE, the XOR of RAND and OPC is first computed, and then the result is encrypted. If AES 128 is used for encryption, then the key can be recovered in the following 2 steps. First, we recover OPC XOR key by a CPA with S-box output in the first round as the attack point. Then we recover the first round key, RQ1, by a CPA with S-box output in the second round as the attack point. Then we can compute key from the round key 1 by reversing the key expansion algorithm and get OPC by cancelling out the key by double XOR. The correlation power analysis was able to successfully recover the key from 300 traces corresponding to the second AES encryption in the power trace and failed on the first one. From this, we concluded that the second encryption is the start of MILENAGE algorithm. We use this part of the trace for training deep learning models. Next, I will briefly review how deep learning is used in the context of power analysis. There are 2 stages, profiling and attack. At the profiling stage, a neural network is trained using labeled traces captured from a profiling device with a known to the attacker key. These traces are captured for random inputs, which are challenges RAND in our case. The labels are selected according to the power model. We used values of S-box outputs, so in our case there are 256 labels. At the attack stage, the trained network is used to classify traces captured from the device under attack with unknown key. Now Martin will tell you more details about our training process.
For both training and testing, we use the CARDIS library in Python to write our code. Due to the choice to use the whole trace in our CNN model, which we will look at soon, the file sizes for our datasets were very large. This meant that we decided to use a high-performance computing system to get around the problem and also to save time. The training could be done on most modern workstations or servers if they had enough memory. Throughout our work, we trained a lot of neural nets. Early on, our focus was on MLP networks. We limited the input to be only the SBox operations for the subkey of interest. Because the USIM cards are 32-bit, the calculations are done 4 at a time, which should make the network performance much worse than 8-bit microcontrollers. Many of our early models were able to successfully recover the byte they were profiling, but we didn't see the types of improvement in attack performance to warrant going through the trouble of using machine learning instead of CPA. We then tried training CNN models on the same data as the MLP models. Some of the CNN models were a little better than the MLP models, but again, we didn't see the big improvements that we were looking for. Eventually, we decided to try training on the whole trace, which improved the performance a lot. We decided to stick with training on the whole round and started being more thoughtful about how we designed our convolutional layers. But why did we decide to train on the full round? There were a few key factors that made us go down that path. At first we were centering our attack window on the execution of SBox operations. The downside of this is that it requires knowledge and experience to identify what part of the trace this corresponds to. A novice attacker would struggle to identify the correct subset of the trace. Second, if you train on the full trace, you no longer need to use an offset in your training and testing code. This, once again, makes the attack simpler. Third, it opens up the possibility of training a network that doesn't require traces to be synchronized. This is yet another way to make the attack more simple. It may even allow for an attack to be done in real time on measurements continuously captured and streamed. Interesting future work could be to create a pattern recognition system that passes the buffer to the CNN if the correct AES encryption is present, thus creating a system that can autonomously monitor and attack a victim. When refining our CNN design, we started off using parameters from past work we had done internally. But after considering the problem, we decided to base our first filter on concrete information about the victim. We knew from earlier attacks on a single block that we could isolate subsets of 900 points from our trace that definitely contained the SBox leakage point. This is why we chose to have such a large kernel for our first layer. We wanted the first processing of the data to have a filter covering all of the relevant data for the leakage point. For all of our convolutions, we were testing either using no padding or using causal padding. We got better results from using causal padding in our limited testing, so we proceeded with using that. We chose causal padding to not create an offset in the resulting output. In total, we used 5 layers of convolutions, followed by pooling to change all temporal data into feature data. After that, we use a single very wide hidden layer before the output layer. We tried using different amounts of hidden layers, but found the most consistently good models had a single hidden layer. This is likely due to the deeper networks overfitting, thus increasing the variance. Here you can see a visualization of the CNN model used in our work. In order to keep the visualization proportional, the first 4 layers have been cropped. Training was done on data captured as Elena described and then synchronized. Here we can see the history for one of the models presented. Because training and validation were both done using traces from one USIM, while the attack is performed on a different USIM, it makes sense to stop training a little early to help generalize. It is clear that it may be possible to train a model that validates better, but our testing indicates that these perform worse when attacking the actual victim. To recover the full key, we would need to train 32 models, one for determining the full round 1 output and one for each subkey. The total performance of such a system is limited by its worst member. This is why we favored hyperparameters that produce reliably good models. With the current settings, the network doesn't always learn. But the benefit of our chosen hyperparameters is that this becomes immediately obvious and training can then be restarted. This could be done with early stopping with a patience of 4 to 5, or manually monitoring the first few minutes of training. Another way of ensuring that learning is successful is to instead retrain a successfully trained network. In order to save time and go more in depth into the separate networks, we decided to only train 3 models. 2 models were trained for round 1, attacking byte 0 and byte 5 respectively of the SBox output. For round 2, we trained a single model to attack byte 0. Previous research on this topic shows little significant difference between the different subkeys, so this should be a good proof of concept. We also made sure to choose 2 bytes that are not calculated in the same interval for round 1. To evaluate the performance of the neural nets, we used the open source tool DLSCA. It comes with a test for calculating and plotting the average rank of the correct subkey for a given number of traces. This means that it's a measure of how many incorrect predictions are deemed more likely by the neural net. Therefore, once the average rank reaches 0, it means that every iteration of the test has correctly predicted the subkey. The tool also stores the raw data for rank progressions, and we use this to also determine the worst case performance and the expected number of traces needed for recovery of the subkey. Here we can see the results for subkey 0 in round 1 for 10,000 iterations of the test. This means that we can be reasonably confident that this specific byte will be recovered within 10 traces. And this is the result for subkey 5 of round 1 using the same test settings. Again, we can see very good performance. Both these models for round 1 always recover the subkey within 10 traces in our extensive testing. In discrete terms, it takes on average 3 traces to recover the subkey bytes of round 1. The actual expected number is around 2.5. Let's move on to the round 2 model. This is the rank plot for our round 2 model. We can clearly see that it's worse. There are many possible reasons for these results to be worse. First, the round 1 traces also include the pre-round calculations. This means that there's a clear difference in the shape of the trace. Second, the hyperparameters used for all of the models were determined by evaluating the round 1 subkey 0 model. This is an area in which immediate improvement is probably possible. Still, the results show that in 10,000 iterations, we always recover the subkey within 20 traces. Since the full system is limited by its worst member, this is what determined our attack's overall performance. The expected number of traces to recover this key is just above 4, but this means that in discrete terms, you need 5 traces to have more than a 50% chance of recovery. There are 2 main problems when doing side-channel analysis on USIM. One is how to properly measure the side channel. The other is how to extract hidden information from your measurements. Tools like ChipWhisperer and Leia have addressed our first issue and lowered the bar a lot. Using them means that sometimes capturing traces from a different USIM card of the same brand is just a matter of running a capture script. One of the things our work addresses is the second problem. How do we make extracting the hidden information easier? With our method, a model can be pre-trained for a specific brand of USIM. Once you have this model, a trace capture script, and the capture hardware we used in this, it is trivially easy to perform the attack. Another thing our proposed method accomplishes is to improve the performance compared to previously published research by an order of magnitude. Because so many fewer traces are needed for the attack, this makes non-synthetic attacks more viable. Capturing the number of traces needed to recover the key can be done in a matter of minutes rather than tens of minutes. It would also make it more reasonable to attack targets in the wild. If you could collect side-channel data wirelessly, you now need only a few authentications compared to hundreds. Furthermore, if future work can improve our results by an order of magnitude, then it would make reliable single measurement attacks possible. We do not claim that our CNN architecture and hyperparameters are optimal. We believe that there is a lot of room for improvement. To wrap things up, I want to address the third focus of our work, viability. We wanted to emphasize a solution that is inexpensive and very easy to operate. If we look at the breakdown of costs of our equipment, you can see that the attack can be done for less than $1,000. This is very cheap for something that could have serious security implications. Furthermore, the equipment is very portable and quick to set up, and the capture of traces is also quite fast. If everything had been prepared ahead of time, it is realistic to remove the USIM from a device, capture 20 traces, and return the device to where you found it in less time than it takes for someone to shower. One thing in particular that makes this attack more viable than other synthetic attacks is that all of the difficult work could be outsourced to one specialist who is a bad actor. Someone could train these models and sell them together with the capturing equipment. And the setup is basically plug and play once you have the scripts prepared. With better generalization, this may no longer be limited to a single brand either. And then we consider that the capturing process could be made easier still. Using pattern recognition, it could be possible to circumvent the need for custom capture scripts or brand-specific capture scripts. then the attacks would no longer require any specialized knowledge at all. It is because of these considerations that we think that machine learning-based side-channel attacks pose a very real threat. Finding ways to mitigate these risks should be a priority. Now we will show a video demo of how to capture traces and then run a test which could easily be translated to an attack script.
Hi, I am Elena Dubrova.
And I'm Brisfors. We're going to show you a demo for the USIM attack.
This is our capturing setup. Over here we have Chip Whisper, which is connected to the computer. This is the Chip Whisper expansion board, and attached to it we have Leia, and inside of Leia we have the USIM card. To capture traces, you just run a custom Chip Whisper script. Sometimes there are issues getting the capture started, but eventually it works, as you can see. Let's also plot the trace so we can see what it looks like.
Now we will do correlation power analysis. I'm starting a script which uses the Hamming weight of SBox output in the first round as an attack point. We can see the process of subkeys recovery in the results table. When all bytes become red color, the whole key is recovered. It will take about 300 traces to recover the whole key. The whole key is recovered now. We can plot correlation coefficients for all bytes. The green lines represent wrong subkey guesses, and the red lines represent correct subkey guesses. We can see distinct peaks, which confirms that SBox output indeed leaks information about the key in this implementation of USIM. Because correlation power analysis successfully recovers the key, we know that this interval of trace can be used for training.
To showcase the attack, we will be using the open source tool DLSEA. We will perform an average rank test. The test calculates the average results of a number of iterations. We will set iterations to 10 to save time. For the set of attack traces, we will use our dedicated attack dataset, which was not only never seen during training, it was captured from a different USIM card. This dataset is comprised of traces that have been synchronized to center on our attack point. In this case, you can see that we are testing key byte 0. For this test to work on other key bytes, you can edit the test code to use an offset of 0 points per key byte. To attack the second round, you treat the round key as the key and the output from mix columns as the plaintext. In an actual attack against a victim card, you would of course not know the value of a key byte. But as the results will soon show, this method quickly and reliably converges to the correct key byte value, so an attacker could determine the key after only a few traces, at most 20 from our testing. And here we can see the results.